Okay, for today's video, we're going to keep talking about compound formula writing and the different forms of that. I just wanted to take a moment and show the periodic table really quick, because I haven't really done that in a video yet up close. When we do compound formula writing, what we are looking at is we are looking at the charges, the valent charges that each group, that is each of these columns, form, ignoring the transition metals. We will talk about some of the transition metals when we talk about multivalent ions and multivalent metals, that those reside in this part of the periodic table here. But most of the simple elements in these two columns here and these 5 columns here, including the noble gases, they have a very consistent valence charge that they have when they undergo ionic bonding. And they all follow a similar trend when they do covalent bonding as well, when they try and get the number of electrons that's necessary for them to have a stable, happy outer shell and bond with other elements. So everything in this column tends to have a +1 charge. Everything in this column tends to have a +2 charge. Everything in this column, for the most part, tends to have a +3 charge, at least here near the top, and this goes the same for the rest of these. They all tend near the top, they follow these trends. Carbon's a little bit different. It could be +4, -4, it could be 0. This row is just, it's a little bit uncertain. It's pretty happy the way it is. It wants to have 4 more electrons added. I'm unsure of the ionic bonding that they do, which is why we don't do a whole lot with it in this row, except for tin and lead when we do multivalent ionic bonding. In the nitrogen group, most things in this group, at least nitrogen and phosphorus, have a -3 charge when they become an ion. Oxygen group here typically has a -2 charge, and in the halogens, fluorine, chlorine, bromine, iodine, and astatine, they all have a -1 charge. Noble gases, this is why they're so noble, they tend to have a 0 charge. They already have a full shell, and only in rare circumstances do they bond with other elements. With that said, we talked about compound formula writing just in the simplest form in a previous video. You can see a link for that, I think, up here at the top. Go watch that if you want to see the basics. We're going to keep going with this video with polyatomic ionic bonding. Okay, so like I said, for this video, we're going to focus on polyatomic ionic compound formula writing. And for this video, we're just going to talk about what is a polyatomic ion. We'll show that really quick, and then we'll show how to, I'll show how to write formulas for compounds with polyatomic ions in them. Let's go ahead, dive right in. Okay, what is a polyatomic ion? A polyatomic ion is just an ion with more than one atom bonded together to form that one ion. Some examples that are pretty common are nitrate, which has a combination of 1 nitrogen and 3 oxygen together. Bonded together, they make an ion that has a -1 charge. There is hydroxide, which typically forms in acids and bases, or at least in acid-base chemistry. This is formed from 1 oxygen, 1 hydrogen, forming an ion with a -1 charge. And then there's carbonate, which typically comes from baking soda, sodium bicarbonate. Bicarbonate being its own ion, but carbonate being a part of that consists of a carbon, 3 oxygens bonding together to make a ion with a -2 charge. There is a ton of polyatomic ions, and there's almost as many of those that would be considered common polyatomic ions. There's no real way to remember all these other than to memorize them or keep a list nearby. I will have a list nearby for all my videos that I make, and I will refer to the list and be given the charges and all that. So I'm not pulling this out of a hat. There is no real trick to keep it memorized other than that if you work with them long enough, you'll probably get it down. Let's go ahead and take a look at how to do polyatomic ionic compound formula writing. Okay, one example that we can look at would be, for example, sodium and hydroxide combining together, hydroxide having a -1 charge, sodium having a +1 charge, and these follow the same exact rules as the simple compound formula writing. The only difference is that we've got an ion with more than one element, and we take an extra step at the end. So following the same steps, we have the charges listed, we have the symbols written out. We'll take a moment, write the charges down below, and what we do is we just check and see, do they even out on each side? We have a +1 here and a -1 here. These are going to bond together to make a stable compound, since these only have one charges, they cancel out really well. Plus 1 minus 1 equals 0. So we would just write it out NaOH. Let's take a look at another example. Another example would be potassium and sulfate combining together. Sulfate consists of sulfur, 4 oxygens, and they combine to have a -2 charge when they become an ion. Potassium, still in the same row as sodium, has a +1 charge. We'll take a moment, we'll write that down. +1, -2. And we got to even up on each side. How you do that? Just add more to the side that has less of a charge. So this has a net 2 charge over here. This only has a net 1, so we're going to add 1 more. 1, 2 equals 2. So we have 2 total potassiums, 1 sulfate ion. We would write that as K2SO4, and then it's good, just as that is. We're going to do a few more examples here. Okay, another example could be calcium and acetate forming a compound together. This is typically what's found in vinegar in the form of acetic acid. Acetate has a -1 charge. Calcium is in group 2, so it has a +2 charge. So we just take a moment. We'll write the charges down here so we can take a look at it. We have a +2. We have a net charge of +2 over here, net charge of -1 over here. So we're just going to add 1 more acetate ion to even that out. So we got 1 here, 1 calcium with +2 charge, 2 acetate ions with -1 charges. That comes out to 2. 2, we're good. So we would just write that. Calcium, there's just 1 ion, so we'll leave that as it is. And to show that we have multiples of everything in here, what we are going to do is we're going to put this whole thing in parentheses. C2, let me write this bigger really quick. Parentheses, C2, H3, O2, 2. Now we write it this way to show that everything in here is one entity. It's 1 ion here that's combining with calcium, and there is 2 of this type of ion that is bonding with this calcium. That's how we write the formula. That's why we include the parentheses. Otherwise, if we just write it like this, we're no longer saying that there is 1 calcium and then 2 ions that has 2 carbon, 3 hydrogen, and 2 oxygen in it. What we are saying is that calcium is bonding with 2 carbon, 3 hydrogens, and 22 oxygens, which is not the case. So that's why we add the parentheses there at the end. And then put a 2. Keep looking at a few more examples. Okay, another example. Ammonium is a positively charged polyatomic ionic compound. It's one of the few examples that at least that I am aware of that you see on a common regular basis, other than hydronium, which we'll talk about more when we talk about acid-base chemistry. Nitrate, another one, we already worked with that earlier. This is just an example if we have 2 polyatomic ions combining to form a single compound. So we do the same thing as we normally would. We put the charges down below, see how it works out. We got +1, -1, we're all good. So you would just write exactly how that is. We're going to take a look at just one more example. Okay, I lied. We're going to look at one more example after this one, but this is just another example when we have 2 polyatomic ions put together, but they have different charges. You could do that method with this one. Just take that 1, put it there, take that 3, put it there, and we'll call it good, but I explained in that other video why I don't really like doing that. So we'll just write down the steps, do it the other way. -3 + 1. This has a net charge of 3. We need a net charge of 3 over here to balance that out, so we need to add 2 more. 1, 2, 3. Cancels out. 1, 2, 3 right here with just that 1 ion. So when we write that, very similar to when we had multiples of a negative ion before, we write the ion and then we put it in parentheses and put a, there's 3 here, so we'll put a 3. And then we add this ion. And that's all good. We're going to take a look at just one more example. Okay, aluminum and sulfate. This is just one of those examples here. Aluminum has a +3 charge if you look it up. Examples where you're going to have more than one type of atom for each one bonding together. Again, you can kind of follow that 3, 2 there, but let's just go ahead and double check it. We got +3 here, -2. So we need to add more sulfate ion here. Add more there. There's 1, 2 to 1, so it's 2, 4. That makes 3 over here. We need to add 1 more over here, 3, 6. 2, 4. We need to add another sulfate ion over here, so it's 2, 4, 6. 3, 6. We're all good. That evens out both ways. So when you write that, go Al2, because there's 2 ions there, and then in parentheses SO4, 1, 2, 3. Again, we put this in parentheses just so that we can show that there is 3 of that one type of ion, not 43 oxygens combining with 1 sulfur. That's just why we write it that way. In another example, if this was, say, another polyatomic ion over here, it had a positive charge of +2. I don't know of any examples off the top of my head, but just for example, if there was just some sort of polyatomic ion that had a +3 charge, we would put that in parentheses as well, so that we would show that there's 2 of these types bonding with 3 of these types. I don't know that example though. I just wanted to show it really quick, just in case you came across it. That's how you would write it. You put both in parentheses and the appropriate numbers next to them. Okay, that's it for today's video. I hope you guys found this helpful. If it was, please like and subscribe, and I'll see you guys all in the next one. Take care.